Thank you, Neeraj, for the introduction, and a big thanks to the organizers for giving me this opportunity, and thank you all for coming here. So today I'll be talking about our work on the symmetries of an equivalence test for design polynomial. So this is the joint work with my advisor, Characterization. So here is the outline of this talk. So I'll first give the introduction to design polynomial, then I'll raise some natural questions about polynomial families, and we'll see the status of these questions for design polynomials, and at last I'll present some of our results. So let's begin. So introduction to design polynomials. So design polynomial looks as follows. So it's the sum of monomials of these kinds. So first of all, the monomials are monomials are multilinear, and if you take a pair of monomials, then they have less number of variables in common. And this is represented by this picture here. And this overlap is upper bounded by a quantity called k. And this is the crucial property of design polynomials, which is called as the low intersection property. Here is a useful example of such polynomial. This is called as Nissan-Wigderson design polynomial. So this is defined as follows. So first you take the finite field fd, which is where d is a prime number and the elements are 1 to d. And then you take the set, then you take the set of univariate polynomials over fd with the degrees at most k. Now, and you take this set of variables, set of d square variables x11 to xdd. Now, what you do, you pick a univariate from this set fd zk, and then you define the monomial as shown in the screen, and then you run the sum over all such univariate polynomials. So this gives you the polynomial, and we polynomial as a Nissan-Wigderson design polynomial. So some observations. So this is a homogeneous polynomial of degree d, and this is polynomial. And the number of monomials in this polynomial are equal to the number of those univariate polynomials, which is equal to d power k plus 1. So in addition to this, this is a set multilinear polynomial. So let me define what it is. So suppose we have a partition on a set of variables, which is say x1 up to xt, where each subset xi contains the variables of kind xij, where j runs from 1 to d. So a set multilinear polynomial is a polynomial where if you pick any monomial, then then that has exactly one variable from each of these subsets xi. And clearly, our design polynomial is a set multilinear polynomial in this partition. So in this talk, whenever I'll talk about set multilinear polynomial, the partition will be fixed to this. Okay. So this polynomial is inspired from the Nissan-Wigderson design, and yesterday in Chi's talk and Anmay's talk, we saw the applications of these designs in details. So I'll not go into this. So polynomial was first introduced in the paper by Kyle, Saha, and Saptharishi, where they prove a super polynomial lower bounds for regular arithmetic formulas. This polynomial was used at several places to prove lower bounds on different classes of arithmetic circuits. So like our design polynomial, there are other classes of polynomials in the literature of arithmetic complexity theory, like the permanent, determinant, iterated matrix multiplication, elementary symmetric polynomials, and power symmetric polynomials, which have been used to prove lower bounds. But we know a lot of things about these polynomials, but almost every question is open about the design polynomial. So one thing that is known and that can be checked easily is that this polynomial is in the class VNP. Okay, so in this project, we aim to study some natural questions about our design polynomial, and I'll come to what these questions are. But just a remark that throughout this talk, I would be comparing the results of design polynomials with the results of permanent. And just for the sake of completeness, recall that permanent look like this, where each monomials come from a permutation on this set T. Okay, so let me go to the second part of which are some natural questions about a polynomial family. So I have clubbed these questions into three categories: structural questions, algorithmic questions, and complexity theoretic questions, and we'll see what these are. Okay, so let's get started with the structural aspects of polynomial. So before raising the questions, let me define a few things, and then I'll raise the question and give the comparison between permanent and design polynomial. So here is the first concept. This is called as symmetry of a polynomial. So suppose you have an n-variate polynomial f, and you treat your set of variables to be a column vector and pick an invertible matrix B. Now I say that this B is a symmetry of this polynomial f if when I multiply x with this matrix B and plug into f, then f remains intact. So in this sense, f is invariant under the action of B. Okay, so before that, so the set of symmetries of f basically is a subgroup of the group of invertible linear matrices, and this is called as the group of symmetries of f, denoted by this notation G subscript f. So let's try to understand this concept with an example. So consider this x1 square plus x2 square, and my vector variable, this vector of variables is x1 and x2 here, and let me pick matrix B. And now when I multiply matrix B with x, x1 gets mapped to x2 and x2 gets mapped to x1, and when I feed this into f, so the f becomes x2 square plus x1 square, which is f. So this shows that B is a symmetry of f. So the symmetries of a polynomials are classified into two categories. The first are called the continuous symmetries, and other are called discrete symmetries. So at this point, I'll not give you the formal definition of what a continuous symmetry is, but we'll see in the later part of the talk. But let me at least try to present this with the help of an example. So consider the same polynomial, f equals x1 square plus x2 square. So first I'm giving the example of continuous symmetries, and to take this real number 0 to 2, okay? A parameter t from this set and your matrix to be matrix bt to be like this. On the diagonal you have cos t, and on the off diagonal you have sin t and minus sin t. Now when I multiply bt with x and feed it into the polynomial, so the polynomial becomes x1 square plus x2 square multiplied by sin square t plus cos square t, and I know that the later identity is equal to 1, so this is a symmetry of. Now observe one thing, that as I vary continuously in this range, I keep getting the new matrices. So for every t, I keep on getting the symmetries in a continuous fashion. So intuitively, this is the meaning of this continuous symmetry. So any symmetry which is not of this form is called as a discrete symmetry, and we saw an example of this. So this permutation matrix was a discrete symmetry of F. Okay, so the natural question arises that, okay, why are we looking into the symmetries of a polynomial? So here are some of the reasons. So because symmetries keep, I mean, you can have continuous functions as well. Yeah, as long as you are getting a series of symmetries. So as the symmetries keep the polynomial invariant, so this is a natural question in invariant theory. And we'll also see in this talk how the knowledge of symmetries of a polynomial actually help us in answering some of the algorithmic questions. So one such algorithmic question which has been looked before is called the equivalence test, and I'll come to the definition of this question later. And as Christian was saying that it is also possible that the knowledge of symmetries actually help us in understanding the underlying polynomial family better. And so this is the GCT approach which he was talking about. And the main goal of GCT is to separate VP from V and P by exploiting one of the properties called the characterization by symmetries of the permanent and the determinant. So let me come to the definition of this property. So characterization by symmetries. So suppose you have two polynomials which are degree D homogeneous polynomials, f and g. So I say that f is characterized by group of by symmetries over the field f if the following thing is satisfied. So I've denoted this with the picture here. So if the group of symmetries of f is contained inside the group of symmetries of g, then this should imply that g is a scalar multiple of that f. Okay, so this is the characterization by symmetries property. And what so it is mentioned in the PhD thesis of Grochow that a random polynomial is not characterized by its symmetries over the field of complex numbers. In particular, what he shows that this property, characterization by symmetry for a polynomial, is satisfied by a very small chunk of polynomial in my polynomial ring. So just a remark here that actually this property bypasses the your natural proof barriers. So by symmetries. That's why it becomes interesting to come up with a lower bounds centered around this property. Okay, so now
does a random polynomial have symmetry?
If a random polynomial is, say, it is a set multilinear polynomial, then it has, but if it is arbitrary, then it only has identity as the with high probability. Okay, so now we have sufficient ingredients to raise the structural questions, so let me go into that. So the first question says that suppose I give you a polynomial, can you tell me if it is characterized by its symmetries over various fields, like fields of complex numbers, real numbers, and finite fields? The second question is an algorithmic question, but again is closely related to the, second question is, what the structure of the group of symmetries of the given polynomial? Or in other words, can you describe all the symmetries of the group of symmetries of F? The third question is an algorithmic question, and but it is very closely related to the symmetries of a polynomial. So it says that suppose I give you a polynomial, say as a list of coefficients, can you give me an algorithm that puts the group of symmetries of that polynomial? And it has been stated in the PhD thesis of Grochow again that this is perhaps a hard problem. But what Burchenko and Olver showed that if you consider special polynomials, for example, if polynomials are binary forms over the field of complex numbers and real numbers, then there is an algorithm for this question. Although I'm not very much sure about the complexity of this algorithm, but this is far better than the brute force algorithm. And the next question is again algorithmic, but very intimately related to the topic we are considering. So suppose, again, the polynomial is given to you as a list of coefficients, and you want to test efficiently if f is characterized by its symmetries. And the open problem mentioned in the PhD thesis of Grochow, and he conjectures this is perhaps a hard problem. So this is the list of the structural questions related to a polynomial family. And let me give you the comparison for some of these questions for a permanent and design polynomial. So first is characterization by symmetries. So it was shown by Mulmule that almost over all the field, it was known that, I'm not sure who is the author, but it was known that this result is yes for permanent for almost all the fields. And but we showed that if you take field to be for design polynomials, if the field is complex numbers, then the answer is yes. But if the field is real numbers, the answer to this question is no. The next question is related to the structure of the group of symmetries. So we basically ask whether the generators of this group are permutation matrices and diagonal matrices. So it is known for permanent that the answer is yes, and show for design polynomial that these are indeed the generators. But indeed, in this case, the permutation matrices have some special structures, which I'll tell you later. Okay, the third question is, since the generators are diagonal in permutation matrices, so it becomes natural to understand them separately. So the next question is, are all the diagonal symmetries known? The answer is yes for the permanent, and yes for design polynomial also over C and R. So this is what we show. And are all the permutation symmetries known? So the complete answer is known for the permanent, and we gave a partial answer for design polynomial. And the next question is, are all the diagonal symmetries continuous? So recall that the symmetries were classified into two classes, continuous symmetries and discrete symmetries. And for permanent, all the diagonal symmetries are continuous, but the answer is different for determinant depending on the underlying, for design polynomial depending on the underlying field. So the answer is no over C, and the answer is yes over R. And actually this no answer helps us in answering the first question over C. Okay, so this is the comparison between these two polynomials. Now let me go to the second class of questions, which is the algorithmic questions. So here is the first algorithmic question. This is called as the circuit testing question. So you are given an n-variate polynomial f, and you want to decide using an algorithm whether when I give you a circuit as an input, does that circuit computes f or not? Okay. So suppose my polynomial is computed by small size circuit, and I just apply Schwarzschild to do this, but it's not clear how to do this when f is not computed by small size circuits. So it makes sense in this regime. Okay, and also one more thing, that actually the knowledge of symmetries are internally exploited by such kind of algorithms. Now here is like one of the reasons why. Now you have this circuit which is fed into the input of this algorithm. Now I know that symmetries keep the polynomial intact, Okay, so now if I apply the symmetries on the that invertible matrix on the leaves of these circuits, so the leaves, the variables get replaced by the linear forms, and when I plug in, the circuit will compute the same polynomial. So my algorithm should not be fooled by this kind of trick. So it should, in that sense, it should have the knowledge of the symmetries of F. And to design such algorithms, knowledge of symmetries have been very helpful. So here is the next question. It is called as symmetry testing. So again, you are given an n-variate polynomial, and you want to decide whether, using an algorithm, that when I give you an invertible matrix, whether that matrix B is a symmetry of F or not. Okay, so here is the third question. This is called equivalence test. So before coming to the question, let me define what equivalent polynomials are. So two polynomials F and G are said to be equivalent if there exists a matrix B over the field F, such that F is obtained from G by replacing a vector of variables by B times X. Okay, so here is the equivalence test question. So you are given a polynomial F, and you want to check if there exists an algorithm which takes input as a black box access to some polynomial G, and then decides whether F is equivalent to G. In addition, this algorithm also, if the answer is yes, it also outputs a certificate for this test. Okay, so if my polynomials F and G are arbitrary, then Agarwal and Saxena showed that this problem is at least as hard as graph isomorphism. But Kyle and then later Kyle, Nair, Saha and Tavenas in their work showed that if F is fixed to be permanent, determinant or IMM, then this equivalence test over C can be solved in randomized polynomial time. In fact, this answer is yes for permanent and IMM over Q, but for determinant over Q, this test is known to be at least as hard as integer factoring. Okay, so here is the next question. So before stating the algorithmic question, let me state the theorem, which is called as the flip theorem for a family of polynomials Fn. Okay, so suppose you have an n-variate polynomial F with a guarantee that it is not computed by the small size circuits, or say the circuits of size S. Then this theorem says that there exists a set of polynomially many points which act as witness, in the sense that if I give you a circuit, a small size circuit, then there exists at least one point in this set such that the evaluation of that circuit and the evaluation of polynomial on that point is different. Okay, and here is the algorithmic question. So I give you this natural number n, and the algorithm should output this list of certificates. Okay, now this theorem is called as flip theorem because it flips this hardness question, which is trying to understand whether a polynomial is computed by small size circuits, to an efficient algorithm that outputs a set of witnesses. So basically it flips this, Sorry? No, SP don't get. So this is true. So say I fix S universally, and then I do this thing. Okay. So this is the algorithmic question, and this theorem, a version of this theorem, is known for SAT. So in particular, what Fortnow, Pavan, and Sengupta showed, that suppose SAT is not computed by small size Boolean circuits, then there exists a set of formulas which will act as witnesses in this sense. And Mulmule proved this theorem for permanent, and he showed that such a theorem holds for the permanent. Okay. And now, next question is called as zero testing on the Boolean hypercube. So the question is as follows. Again, you have an n-variate polynomial F, and what you want to check if there exists an algorithm A which takes a point from this Boolean hypercube and decide whether the evaluation of F at that point is non-zero or not. Okay. So this is also related to the circuit complexity of F in the following sense, that suppose the answer to this question turns out to be hard, okay? Then an immediate implication is that F cannot have small size uniform circuits, but because then this will violate the hardness of this result. And in case of the design polynomial, this problem has some connection with hardness amplification problems, which were noted by Bogdanov and Safra in their work, okay? So now we have all the algorithmic questions, and now let me talk comparison between design polynomials and permanent. So circuit testing algorithm was known for the permanent. We gave this algorithm for the design polynomial. For permanent, symmetry testing algorithm is known, and for the case of design polynomials, we showed we gave the complete answer to this question for diagonal matrices and a partial answer for permutation matrices. Now recall here that we know that the generators of the group of symmetries of design polynomials are actually the diagonal matrices and permutation matrices. Okay, so Kyle gave the answer for equivalence test, and we have partial answer for design polynomial over reals and finite. In particular, we have answers when the invertible matrices are of special kind of permutations and scaling matrices. So I'll come to this at the later part of my talk. Okay, so the flip theorem is known for the permanent, and we proved the flip theorem for design polynomials. And zero testing is known for permanent, but this is an open question for design polynomials, and this was mentioned in the work by Bogdanov and Safra. So at this point, let me stress on the fact that actually many of these algorithmic results crucially rely on the knowledge of the group of symmetries of F. So the structural properties do help in designing such kind of algorithms, and we'll see it after some time, case of design polynomials. Now let me quickly come to the last category, which were the complexity theoretic questions. So the first question is whether a polynomial is VNP complete, and the second question is called as the circuit compression question. So this is stated as follows. So you have a polynomial f which has m many monomials, and you want to decide, the question is, can f be computed by a circuit of size which is far smaller than m? So the answer to both these questions, or both these questions are open for design polynomials, but answer to both these questions are known for the permanent. And in case of the circuit compression, actually the number of monomials in permanent are n factorial, but we know a 2 power order n size circuit computing permanent. So that's it. These are all the three classes of questions. And let me present the proof of some of our work for design polynomials. And in particular, I prove the symmetry characterization result. Oh, sorry. In particular, I show that I prove the symmetry characterization, show the structure of the group of symmetries of design polynomials, and special cases of equivalence test for it. So just excuse me. So any questions so far? Okay. So here is the first theorem. So we showed that design polynomials is characterized by its symmetries over the field of complex numbers. In particular, recall the definition of the characterization by symmetries. And in particular, we showed that if f is a homogeneous polynomial of degree d over the field of complex numbers, if the group of symmetries is sitting inside the group of symmetries of f, then f is actually a scalar multiple of design polynomials. So again, quickly recall the definition of symmetries and Arnisan and design polynomials. Now, before giving the proof of this theorem, I'll actually show that there exists some non-trivial symmetries. By non-trivial symmetries, I mean the invertible matrices other than identities. There exist non-trivial symmetries for design polynomials, and these symmetries actually help us in proving this theorem over C. So here is the symmetry of first kind. So these are called as continuous diagonal symmetry. So these are diagonal matrices where the first every matrix here is d square cross d square, and in this types of matrices, the first entries are alpha 1, first d entries are alpha 1, next d entries are alpha 2, and so on. And each of these alpha i's are basically non-zero complex numbers, and the product of each of these alpha i's is equal to 1. Okay, so let's try to convince ourselves that this is indeed a symmetry of the design polynomial, and it is sufficient to look it for one monomial because of the linearity of this action. Okay, so let me pick this monomial corresponding to the univariate polynomial h. Now when b is multiplied to x, so basically this monomial gets mapped to the product of alpha 1 up to alpha d, and then x1 h1 to x dht. And we know that this product is actually equal to 1. So then the coefficient becomes 1, so monomial is mapped to itself. So this shows that B is a symmetry of the design polynomial. So now why called continuous symmetries because we can vary these alpha 1 to alpha d minus 1 in a continuous fashion, and then alpha d is fixed accordingly. Okay, so this is the symmetry of second kind. These are called as the permutation symmetries. So you pick a univariate polynomial q from this set fdzk. Recall that this was the set of all univariate polynomials with degree at most k over the finite field ft. Now you define this matrix in such a, when you multiply it to this vector of your variables, the variable xij gets mapped to xij plus qi. Okay, and it is easy to check that this is a permutation matrix. Now let's look let's again convince ourselves that this is a symmetry of the design polynomial. So again, pick this monomial corresponding to the univariate polynomial h, and when I multiply bq to x, actually this monomial gets multiplied to the monomial obtained by the univariate polynomial h plus q. Now since h and q both are degree at most k polynomials, this is again a monomial of design polynomials. So this shows that bq is again a symmetry of design polynomials. And now let's come to the symmetries of third kind. These are called as discrete diagonal symmetries. Again, the matrices are diagonal d square cross d square. So what we do, we pick alpha, which is a dth primitive root of unity, and we pick L from this range 0 to d minus k minus 2. And then what I do, I define my matrix like this, where the ijth diagonal entry is alpha power I power L times j. Okay, now let's again see if that this is the symmetry of this polynomial. So again, I pick a monomial, and when I multiply BL to this x, so basically this monomial gets multiplied to itself with some constant. So this constant is a product certain each shown that if h is a degree at most k polynomial and n is in this range, then this product is equal to 0. So monomial of Nissan-Wigderson under this section is getting mapped to itself. So that this is a symmetry of design polynomials. And this is actually the place which uses the complex numbers because we need alpha to be the dth root of unity. And such symmetries are not present over the field of real numbers. So we come to the theorem. So we wanted to show that design polynomial is characterized by symmetries over the field of complex numbers. So suppose there was this homogeneous degree d polynomial f such that the group of symmetries sits inside the group of symmetries of f. Now, the continuous diagonal symmetries of design polynomial implies that f is a set multilinear polynomial with respect to the partition we defined before. And the other two symmetries imply that f is a scalar multiple of the design polynomial. So this completes the proof of this theorem. So before going further, let me make a remark here that actually these polynomials are uniquely characterized up to scalar multiple by this property, if they by this property. And what we also show that if we switch the field of complex numbers to this field of real numbers, then this answer also switches from yes to no. So we show that Nissan-Wigderson is not characterized by its symmetries over R. So I'll not be talking proof of this, but if you is interested, maybe we can talk offline. Okay, so now let me go to the second, yeah. Okay. Okay. Yeah. So I can, maybe offline I can tell you the polynomial. So we have a polynomial which doesn't look like alpha times Nissan-Wigderson, but it contains, yeah. So this actually helps us in proving this theorem over R, because over R we don't have discrete diagonal symmetry. Yeah, okay. So now let me go to the second result, which is related to the structure of the group of symmetries of design polynomials. So we prove the following theorem, that every symmetry of design polynomial is a product of diagonal matrix and a permutation matrix of special kind. And this permutation matrix is actually a block permuted permutation matrix, which looks like this. So maybe spend some time to see this. So we first have these smaller blocks which are permuted, and then if we look into these blocks, these are further permutation matrices. Okay, so we show that F is a product of D and a matrix of this kind. Okay, so here is the proof idea. So we first use the Lie algebra of design polynomials. Again, I'll come to what Lie algebra is, but just bear with me for some time. So we first use the Lie algebra of design polynomial to show that every matrix or every symmetry of it is actually a block permuted matrix. And then further we use the Hessian of design polynomials and evaluation dimensions to show the result. Okay. Now let me come to what a Lie algebra of a polynomial is, and we also have completely characterized the Lie algebra of design polynomials, and then we'll see some algorithmic applications of this. Okay. So here is the definition of Lie algebra of a polynomial. So how much time do I have? Okay. 10 minutes, okay. Okay, so suppose I have an n-variate polynomial f, and I have an n square cross n square matrix A where the ijth entry is Aij. So now I say that this matrix is in the Lie algebra of f if the following equation is satisfied. So what you do, you first take the first order partial derivative of f with respect to xi, then you multiply it with xj, and then further multiply this with the ijth entry of your matrix, and then you sum over all j's and then equate it equal to 0. So any matrix satisfying this is in the Lie algebra. So it is easy to verify that this is a vector space over f, and as before, let me give you the formal definition of continuous symmetries of a polynomial here. Okay, so we have Lie algebra of what we do, pick a matrix from it and then apply and look at the exponent of this matrix, which in the the Taylor series expansion is just 1 plus a square by 2 factorial and so on. Now this can be shown that such kind of matrices are the such kind of matrices are called as the continuous symmetries of F. So it can be shown that such kind of matrices are indeed inside the group of symmetries of F. Okay? So this is the theorem which we prove related to the Lie algebra of design polynomials. So we show that if you pick a field to be such that the characteristic F is not equal to D, in particular it holds when characteristic of field does not divide D when is no longer a prime, then the dimension of the Lie algebra of design polynomial is equal to D minus 1. And the matrices of following kind form an F basis of this Lie algebra. So let's see how these matrices look. So in the first matrix B1, I have first D entries on the diagonal as 1 and last D entries as minus 1 and other entries as 0, and this repeats for other matrices depending on the attached index. Okay, so surprising thing is that the Lie algebra of design polynomial is contained inside the Lie algebra of any set multilinear polynomial. So shown these matrices are inside the Lie algebra of any set multilinear polynomials. So in this sense, our design polynomial is trivial, that we don't get anything extra in terms of Lie algebra from here. But what we will see is that apart from this constraint, the structure of design polynomial is rich enough to imply results. And here I would like to go to the next question. Before that, let me quickly, I'll not sketch the proof of this, but I'll give the most crucial insight of the proof. So basically this proof relies on solving the equations of these kinds. Let me tell you what these equations are. So you pick or you fix these formal variables, formal d square variables gamma ij, where ij run over fd, and then you pick a univariate polynomial h and then define this equation like this, where gamma 1 h1 plus gamma 2 h2 and so on, and equate it to 0, and you club all such equations together, and so there are d power k plus 1 many equations in this system. So what we show crucially that the dimension of the solution space of this system is equal to d minus 1, and the solution space of this system of linear equations is actually the Lie algebra of design polynomials. So now let me go into the third questions and the last question of this part, which is the equivalence test for design polynomials. So recall that equivalence test problem looked like this. So we wanted to know there exists an algorithm that decides whether a given black box polynomial is equivalent to the design polynomial. Okay, so here is the crucial lemma. But we showed that your general equivalence test, by general I mean that this matrix B, which basically acts as this certificate of equivalence, when this is an arbitrary invertible matrix, then we can actually reduce this test in randomized polynomial time to the test of the following kind when this matrix B is an invertible block permuted matrix, which looks like this. So you have these smaller blocks which are permuted. These smaller blocks are invertible matrices, smaller invertible matrices in themselves. And this lemma is proved using the Lie algebra of design polynomials. Okay? So I'll talk about some special cases of the equivalence tests which we have so far for design polynomials, and these are the block diagonal PS equivalence tests. So here P stands for the permutation matrix and S stands for a scaling or a diagonal matrix. Okay? So we are basically, we answered a question whether your polynomial F is equivalent to the design polynomial via this matrix B, which is now a block diagonal matrix. And further, if we look into the diagonals on the blocks, these are the product of smaller invertible diagonal and permutation matrices. So this is what we call as block diagonal PS equivalence test. And again, so let me quickly go over the proof of this test. So we solved this test in 2 steps. We first solved the scaling equivalence test for this, and then we solved the block diagonal permutation when the blocks on the diagonal are now permutation matrices. Okay, and let me stress on this fact again that actually these results are implied from the knowledge of the group of symmetries of design polynomials. So this is how actually the structural properties like group of symmetries help a lot in designing algorithms. Okay, so now let me go into the proof of this. So the goal is first to solve scaling equivalence test for design polynomial, and our result actually holds over real numbers. Okay, so this is the goal. So there is this theorem by Blazer, Rao, and Sharma, which says that if you have 2 polynomials as black boxes, say f and g, then there exists a randomized polynomial time algorithm which takes input as black box of these polynomials and checks efficiently in randomized polytime if f is scaling equivalent to g. Okay, but in our case, we do not know how to use this theorem as we don't have black box access to the design polynomial. But still, I mean, using the structural properties of design polynomials and the properties of real numbers, we could answer this question. So here is the idea. Suppose this underlying matrix B, which acts as a certificate for equivalence, looks like this. So it is a diagonal matrix where I have split the absolute value part and the sign part of this. Okay, and now because my f is equivalent to the design polynomial via this matrix P, so let's look at the action of this on a design polynomial. So let me pick a monomial which corresponds to the univariate polynomial H, and when I multiply B to X, then this monomial is multiplied to itself plus some coefficients. Again, I have split the coefficient into 2 parts, the sign part and the absolute value. Now, because of this relation, the following equation should hold. So first is the equation for the absolute values, or the power, 2 powers the absolute values, and then second is the equations for sign. And actually, we answered this using the knowledge of the system of linear equations, which actually helped us in understanding the Lie algebra of design polynomials. So the first system is solved over reals, and the second system is solved over finite field F2. So let me quickly come to the second part of this proof, which is to show, to give algorithm for block diagonal permutation matrix. So I'll not give the complete proof, but I'll stress on this fact that how actually the knowledge of symmetries help us in getting a handle on such kind of matrix. So to begin with, I only know that B is a block diagonal matrix where on the blocks these smaller permutation matrices are sitting. So actually with the help of symmetries, what we can assume without loss of generality that on the first k plus 1 blocks on the diagonal, I can assume certain entries to be 1. Okay, and then I query my black box wisely and I recover all of these matrices. Okay, so I'll not go into this as there is no time. So let me come to the open questions. So the knowledge of all the permutation series of design polynomials is open, and we also don't know the complete equivalence test for it. In particular, we don't know the block diagonal equivalence test, where the underlying matrix is now a block diagonal matrix, but these smaller matrices are arbitrary invertible matrices. The case which we saw, these smaller matrices were the product of diagonal and permutation matrices. Then we don't know the zero testing, circuit complexity, and circuit compression of design polynomials. Now, before closing, let me come to one of these questions, which is the zero testing question of design polynomial. So recall that this question was this: we want to design an algorithm which takes a point from Boolean hypercube and answer 1 if the evaluation of design polynomial at that point is not equal to 0, 0 otherwise. Now, this is a d square size vector. This A is a d square size vector. So this looks like this, where the first d entries has some ones and some zeros, next d entries have some ones and some zeros, and so on. And I write the first d entries as A1, other next d entries and A2, as so on. And now using these subvectors A1 to AD, I define the sets like this. So for each I define this set Si, which is a subset of D. So these contains all the elements from such that the jth element picked from this set Si, the jth element or the jth entry of this vector Ai is equal to 1. Okay, so this is the setting for zero testing in terms of. Actually, their coding theoretic view to this question, which is as follows. So suppose somebody gives you these subsets of this set D, S1 to SD, and you want to find whether there exists a polynomial H which has a degree at most K, such that for every field element, the evaluation of that polynomial H of L should be contained in the associated set SL. And just for the sake of pictorial representation, I have drawn this polynomial like a curve, which cannot be drawn over a finite field, but this says that if you look at the different evaluation points, then the later part, this H1, H2, should be, this should be H of 1, H of 2. So these should be, so for every L, HL should be contained in the set SL. So that's it. I close. Thank you so much.